This tutorial is going to cover solving and constructing simultaneous equations. In particular, we're looking at the geometry of simultaneous equations, i.e. unique solutions, no solutions, and infinite many solutions. And this is found on page 6 of your notes. What we mean by the geometry of simultaneous equations is looking at graphically what's in common, what's different, what's special, or what can we make special about simultaneous equations. So we have 3 different cases that we in particular look at. We look at unique solutions, no solutions, and infinitely many solutions. This is really important because although it's not taught at Year 12, it is definitely expected notice, and about every second year there are exam questions with relation to the geometry of simultaneous equations. Alright, so we're going to look at a case of each of these, and then how can we show that something has a unique solution, for instance. Let's start here. Unique solutions. The 2 lines shown here, so these 2 lines here, have a unique solution. By unique solution, we mean that they have exactly only one intersection between them. So if I was to solve this, I would get out an individual point. For this to be the case, so for a unique solution to exist, the gradients must be different, and the y-intercepts, it doesn't really matter what they are, because you could have a unique solution that is in fact your y-intercept. So this here is a unique solution. An example for this. We're asked to show that the following has a unique solution. To show that it has a unique solution, what we need to do is show that the gradients are different, and it doesn't really matter what the y-intercepts are. So what we're really doing is show that gradients are different. To show that the gradients are different, your easiest method to do this is to convert each of these equations into our general form, which is y equals mx plus c. Okay, name your equations. That's step 1. Step 2 is I'm going to rearrange into y equals mx plus c, and I can put form there. Equation 1. Equation 1 starts off as 2x plus y equals 5. Rearranging this, I'm going to get rid of that 2x from both sides. It's going to leave me with y equals minus 2x plus 5. So that's in the right form. For equation 2, I'm starting with x minus y is equal to 4. I'm going to plus y and then minus 4 from both sides. Which will give me y equals x minus 4. Both of these are now in the form of y equals mx plus c. And using this, we can read off what our gradient and what our y-intercept is. For any question relating to the geometry of simultaneous equations, you are best to always write down both your y-intercept and your gradient, or gradient and y-intercept in this particular case. So M1 and C1, I'm going to actually rename this as equation 1 and equation 2, well, not rename it, but highlight that it is. So M1 is going to be equal to -2, and C1 is 5. Remember, your M value is that whatever you multiply that x value by, and your c value is whatever's tacked onto the back. Let's do the same thing, but let's do it for equation 2. M2 is going to be equal to, well, what's in front of that x? We multiply by it, but we don't write it. That is a 1. And the C1, or C2, sorry, is going to be equal to -4. For a unique solution, we're interested in M1 and M2. For there to be a unique solution, these two cannot be equal. As this is the case, we can say there is a unique solution. That's all you need to do. Basically, by showing that our gradients are not the same, we can say quite definitively that there is a unique solution. Box that as that is our answer. To show that question, actually, the entire thing's our answer. Let's not box anything, because to get full marks for that sort of question, you would actually need to have all of that there. You would hopefully rule this line, but let's look at no solutions. No solutions are essentially parallel lines. This is the case where the two graphs or equations do not meet ever. There is no intersection at all. What this means is that the gradients must be the same, i.e. parallel lines, but the y-intercepts must be different. We can't have two lines with the same y-intercept and there to be no solutions. We'll look at that case in a second where the y-intercepts are the same. So for no solutions, gradients are equal, y-intercepts are different, i.e. gradients are equal, y-intercepts are different. Might just add to this past one, gradients are different. Okay, let's have a look at the example for this. We want to show that the following has no solutions. Our first steps are exactly the same as what we've previously done. Name the equations, equation 1 and equation 2. We want to rearrange into y equals mx plus c form. Taking that first equation, we've got 2x plus y is equal to 5. The second equation, 2x plus y is equal to 7. Rearranging this, we will get y equals minus 2x plus 5, and y is equal to negative 2x plus 7. So two equations in the form of y equals mx plus c. Let's identify our our gradient and our y-axis intercept. Our gradient for equation 1 is negative 2. Y-intercept is going to be 5. For equation 2, the gradient is negative 2, and the y-intercept is 7. For there to be no solutions, then M1 must equal M2, and C1 must not equal C2. Change that to a 2, sorry. This is correct, as M1 is negative 2 and M2 is negative 2, i.e. they're equal, so we can say that's correct. Our next property of C1 not equaling C2, well, C1 is 5, C2 is 7, those are not equal, which means that that property holds. Therefore, no solutions. No solutions to this simultaneous equation, or these simultaneous equations. And the last case. The last case is the case of infinitely many solutions. Infinitely many solutions are essentially two copies of exactly the same line. The equations may not start off looking the same way, but essentially our gradient and our y-intercept must be the same, i.e. m is going to be equal to m and c is going to be equal to c. So they're exactly the same thing. This example will show that the following has infinitely many solutions. First step again is going to be to rearrange this. If you can show that they're the same equation, i.e. by dividing this second equation by 2, you would be actually capable of saying, therefore, there are infinitely many solutions. I'm going to use the same property we've used previously, because there's different forms of this question that still require you to find the gradient and find the y-intercept. First step, equation 1, equation 2. We are going to rearrange into y equals mx plus c form. For equation 1, that will look like, well, we'll start with 2x plus y is equal to 5, minus the 2x from both sides, and y will equal minus 2x plus 5. Equation 2 will start off with 4x plus 2y is equal to 10, minus the 4x from both sides, and we'll have 2y is equal to minus 4x. I'll just move that across. We'll have, 2y is equal to minus 4x plus 10, divided by 2, and y is going to be equal to negative 2x plus 5. Obviously, you can see at this point those are exactly the same equations, but we'll go through the process of identifying our gradients and our y-intercepts. So gradient of negative 2, y-intercept of 5. Same for equation 2, minus 2 and 5. For there to be infinitely many solutions, m1 must equal m2, and c1 must equal c2. So our gradients and our y-intercepts must be equal. They are, therefore, infinitely many solutions. Done. So again, we haven't boxed anything, as I show that question includes all working out. It is important that this concept becomes very clear, as we will approach it a little bit later, but we're not actually going to re-go over this next year, or in 2017 when you're in Unit 3-4. That concludes this tutorial. The next tutorial will be on constructing simultaneous equations.